interval, we're integrating over a region in the XY plane. All right. We're going to talk about how that looks a little different. But that's the definite integral. So this first part, we're not going to do that right now, but we're excuse me. We're not going to do the Riemann sums, so don't worry about that. But I want to talk about basically what's going on in 14.1. And then in 14.2, the main thing I want to focus on is when our regions aren't rectangular. When our regions are rectangular, things are pretty straightforward. And so what I mean by this, we're integrating x squared plus y squared. So that's the function over some region in the xy plane. And that's the region is given by here. X is going from 1 to 2. Y is going from 1 to 3. So one of the things we'll look at today is actually sketching our region of integration. So this is being our x, this being our y, because we can do this for double integrals. When we get to triple, it's going to be a little trickier, but that's why we want to spend the time getting double integrals down, so that when we get to triple integrals, it's only adding an extra layer. So we're seeing that x goes from 1 to 2, and y is going from 1 to 3. So this is what we would call our region of integration. When it's a rectangle, it is very easy to set up our definite integral. The order does not matter. All our limits are going to be constants. It makes for a very easy double integral. Now, when we go to work a problem, there might be an order that's easier than another order. Like we wanted to use U substitution or something like that. We may want to do integrate with respect to x first or y first. But in general, setting it up, we can set it up either way. And on an integral like this, the order really doesn't matter. So we're integrating over x squared plus y squared. And let's say we decide to do x first. X is going from 1 to 2. And so we put that at the end of dx, all right, because this tells us the order. And then in terms of y, 1 to 3. And that would be the setup for our double integral. And then we would calculate this. Now, this goes exactly the same way that the partial derivatives did, just the other direction. So if I'm integrating with respect to x, y is a constant. So my antiderivative would be, now we're not doing y yet, but we're going to have x cubed over 3 plus y squared times x, because remember y is a constant, so y squared is a constant. And then that's going from 1 to 2. And then we'll still have to integrate with respect to dy. So now you put your limits in just like you would your fundamental theorem of calculus. So we're going to have 1 to 3. We're going to be putting in the limits 2 and 1. Remember, we integrated with respect to x. So these are x values. Okay. Y is still going to be in there. So we have 2 cubed over 3 plus y squared times 2. Just to keep those separate, let's put parentheses around them. 1 cubed over 3 plus y squared times 1. And then we'll simplify this as much as we can. And at that point, we're down to a single variable integral. We're down to a Calc 1 problem. So 1 to 3, let's see, we're going to have 8/3 plus 2y squared minus 1/3. I'm just going to distribute this negative all at once, minus y squared. dy. You can do the antiderivative here, but we might as well combine like terms first. Yep, so we can see the 7/3 for a fraction, and then 2y squared minus y squared is just a plus y squared dy. And now a single variable problem, 7/3 y plus y cubed over 3 from 1 to 3. So 7/3 times 3 plus 3 cubed over 3. So I'm running out of room here. Minus 7/3 times 1 plus 1 cubed over 3. And let's see, that's a lot of this is going to simplify. Those will cancel. We're going to end up with 8/3 there. Or sorry, that's a minus 7/3 plus a third. So what do we got? This is going to be, that'll be 9. So we got 16 minus 7/3 plus a third. So that'll be a minus 6/3 or minus 2. So when all said and done, 14. So I wanted to go through a whole one where, we actually went through the process of doing the antiderivatives. And a couple things I want to point out, and we'll point out, I'll be a little more emphatic about these in the next section, but the last set of limits always has to be constants. Otherwise, we're not going to get an answer. Not a big deal on this one because all our limits were constants. Just like with partial derivatives, you have to focus on one of your variables being a constant while you integrate with respect to the other, and you have to do your fundamental theorem. Again, now this is our easiest case when our region is just a rectangle. Questions about this one? So, like I said, you're going to get a chance to practice this here in a little bit. Just a couple interpretations of the double integral. So just like in single variable calc, we use a double integral to calculate area under a curve. These could calculate the volume under a curve above the region. So in this particular example, we've got our paraboloid here, and that paraboloid is coming out of the board like this. This is the region in the XY plane. What we calculated was the volume that's underneath our paraboloid that sits inside this square region. So you can imagine a block going up to the paraboloid that calculates the volume under the surface and above the XY plane. So it's analogous to what we saw in single variable calc. So that's one interpretation of the double integral, is if we're integrating over a function, we're finding the volume underneath that surface and above the XY plane within the given region. Now, if we let the integrand be 1, then what we're actually calculating is the area of that region. For example, if we didn't have a function here, if this was just 1, all this is going to do is calculate the area of that rectangle. Because we're going to have 2 minus 1 times 3 minus 1 for the area of that rectangle, which is 2. And lastly, we can do also average value. So this is very similar to average value of a function in single variable calculus. In single variable calculus, to do the average value, you do the integral of f of x dx from a to b, and you divide by the length of the interval. Now, in multivariable and a double integral, to do the average value, you do the double integral over your region, and then you divide by the area of the region. So if we wanted the average value of this function over this region, we would divide by the area of the region, which is 1/2 rectangle. So if we took 14 over 2, 7 is the average value of the function over this region. Right? Because what's happening is this surface is not flat over this region, right? It's some paraboloid that's opening upwards. Well, the average value, the average z value over this region is 7. That's what it's saying. And it's nothing more than doing the double integral and dividing by the area of the region. So those are just some interpretations of the double integral. Questions at this point?